Hello, everyone. We are going to be getting started in about 2 minutes here. Hello, and thank you for attending today's webinar with Test Oil. We are going to be covering how to use oil analysis to identify improper lubrication. My name's Heather Russillo. I'm a CLS with Test Oil, and I'll be hosting the webinar today. Today, Evan Zabowski will be presenting for us. And Evan is a certified lubrication specialist, and he has extensive experience training tradesmen and professionals in a variety of fields that include lubrication fundamentals, contamination control, condition monitoring, RCM, FMEA, and used oil analysis. And he has been a member of STLE for over 20 years, and he serves as the chair of the Alberta section for 8 years. And he's also an instructor of the condition monitoring courses at the annual meetings. Currently, Evan is the editor of TLT magazine and has served for the editor for the Alberta section's Basic Handbook of Lubrication, the 3rd edition. And he's also contributed as one of the editors for the STLE CRC's Handbook of Lubrication and Tribology, Volume 2, Theory and Design. And Evan has been with Test Oil for a number of years. He is our senior technical advisor and presents most of our training sessions, and he is a wealth of knowledge. So during this webinar, if you have any questions or points of discussion, please feel free to put them in the chat or the questions section. Or if you're even having any technical difficulties, I can help you on the side. With that, I'd like to pass over to Evan, and you can go ahead and take it away.
All right, thank you, Heather. So today's presentation about using oil analysis as a tool to identify improper lubrication mostly came out of a common graph many of you have probably seen if you've attended similar presentations or webinars. It looks like this, and it just summarizes bearing failures by type. And as you can see, the largest slices of the pie are related to either the lubricant directly or a contaminant. And that's kind of the common thread that we find with many lubricated systems, is that the findings of most oil analysis tend to relate to either contamination of said lubricant or possibly some improper uses or mixing of lubricants, these kinds of things. So oil analysis is a great tool, and I'm trying to use this presentation to show you how you can identify a fairly common problem, but using a bit of an unconventional way to do it. So what we're going to talk about is how wear metals and additives are measured, and that's going to be very, very brief because I usually do that as a completely separate webinar. And for the benefit of those who haven't seen it or heard something like that before, we'll just quickly review it. Same thing goes with particle counting. Again, that's another webinar that we've done, but I'll just review that so we hit the high points so everyone knows kind of what we're talking about with those two tests. And then just a little bit again briefly on analytical ferrography so that you have an understanding when we actually get to reading a report what we're looking at. Once I've gone over those brief reviews, I will then show you what I call the unconventional steps to reading a report, because this is how you should go about reading oil analysis reports. And most people either don't know how to do it this way or just don't take the time to do it this way. And it's actually much more efficient than usually the way people sort of dance around and look at all the highlighted numbers and try and figure out where everything's sourced from. So I'll go over those steps and then we'll actually do a real case study. So this is an actual report and we'll review it. We'll look at things, we'll follow my steps and we'll see how it goes. Before we get to our final verdict though, I'm gonna have a short little story to help give you a reminder. Keep things simple. The simpler it is, the easier it is to come up with the right answers. And then I'll give you another reminder why the end user must be the one to do this step. Because a lot of people ask that question when it comes to sending oil samples to a lab, is why can't the lab absolutely pinpoint accuracy tell me the problem? And sort of the reason behind that is they don't know everything. They know a lot, but they don't know everything. So I'll give you a couple of reminders there, and then we'll settle on the actual verdict. At the very end of the presentation, you'll see what went wrong. So to begin, how wear metals are measured. This test is called elemental spectroscopy. The test is fairly straightforward in the steps. So briefly, to review, we take a sample, we dilute it with a solvent, and we introduce it into a plasma. That's what you see pictured there. The sample comes in from the bottom of the plasma and is sprayed into the plasma as an aerosol. So basically, we're misting your sample diluted down with a solvent. What happens though is as the sample enters the plasma, it's ionized. For lack of a better word, think of it like burning. But the plasma ionizes the sample, and when things are ionized, they give off light. And every element on the periodic table has a spectra of light that it gives off, different wavelengths of different color, and each one is unique to each element. So what we do is we look at certain wavelengths of light and we can tell you what element is there, and then by how bright the light is, we can tell you how much of the element is there. And that's why we call it elemental concentration. Keyword being element. It doesn't tell us that it's brass, it tells us that it's copper, tin, and lead. And concentration, it gives it to us in parts per million in the sample. So to give you a kind of a visual of what the instrument sees, if I was to introduce a sample that contained aluminum, tin, and lead, these would be the individual wavelengths of light that would be seen by the instrument. And as you can see in the top right corner there, there's a bandwidth of red that appears in aluminum, but does not appear in tin, does not appear in lead. So if we were to analyze how bright that bandwidth of red is, we could determine what the concentration of aluminum would be in the sample. So like I said, simple steps, is complex instrument, sure, but basically we're just trying to light up the sample and we can see what's in it. Now, one key point though about this test is that when the test is being performed, it is an aerosol. These are tiny droplets. We have to ionize them. Not everything ionizes within the plasma. It has to be introduced into the plasma, has to ionize within that small window of opportunity. So that's why we have the statement here that it measures 0 to 5 micron particles accurately. After 5 microns, the accuracy takes a bit of a nosedive, and particles beyond about 10 microns are really undetected. And that's largely because the aerosol droplets are in the neighborhood of about 15 microns. So if the particle is much larger than 10 microns, it won't stay suspended in the droplet and it won't get misted into the plasma. So it's not even there. It doesn't even get introduced into the instrument. But this is a point of contention that you'll see as we read through the report. A lot of people don't know this. They don't know that when we analyze for wear metals and additives and contaminants using this test, that not everything shows up. Only the things in the 0 to 5 micron range show up accurately. Anything a little bit larger than that is less accurate. And like I said, around 10 microns, it doesn't show up at all. Now as well, I'll point out that it does have a couple of interferences. When we introduce the sample into the instrument, as I said, the first step is we must dilute it. Well, not everything dissolves in the diluent that we use. So sometimes some things don't show up. Another issue which won't affect us today in the particular example I have, but just to cover this base, water content also causes some issues. And that's because water, when it ionizes in a setup such as this one, it causes the plasma to sputter. So basically the plasma wiggles. And that plasma wiggling reduces our accuracy of measurement, so it can throw off numbers. Now, thankfully, the example today doesn't have high water content, so we won't have to worry about that, but just in future, if you ever had a really wet sample get submitted to a lab and you wonder why the results looked weird, water could be a predominant factor in the inaccuracy of that test. But just to cover a couple of the parameters measured by this test, let me point out the first of two, calcium. Why does calcium show up in an oil analysis test for elemental spectroscopy? Well, calcium is most commonly found in oils as an additive. And my point here is that when you see calcium as an additive, you should allow at least a 25% deviation from the new oil baseline before you start to get too reactive to it. The reason for this is twofold. One side of the coin here is that when we blend oils at a blending facility, there's at least a 10% allowance, wiggle room tolerance, whatever you want to call it, between batches. So there's a little bit of variance from batch to batch. So you have to allow that 10%. But there's at least, again, another 10% inaccuracy to this test in terms of repeatability. So we have to compound that on top of the other 10%. So that's why I say at least 25%. What I mean is that if the new oil baseline says it's 100 parts per million, as long as it's between 75 and 125 parts per million, that is really the same number. And that is the same oil. You can't call it a different oil. You can't suggest it's got a mixture or anything like that. The other element that I'll point out, just to get everyone on the same page here, is phosphorus. Phosphorus is also most commonly found in oils as an additive. It appears only in two types of oil, though, AW, anti-wear oils, or EP, extreme pressure oils. And again, we should allow 25% fluctuation on that value from the new oil baseline before we suspect there's a different oil or contaminant in here. Now, something else as a reminder is that when we talk about anti-wear oils, the most common anti-wear additive is ZDDP, and that would contain relatively equal parts phosphorus and zinc. EP oils typically use a sulfur phosphorus chemical, and we don't measure for sulfur, so we would only see the phosphorus. That's why I say phosphorus only here. But if somebody says it's an R&O oil, the type of additives that are used in R&O oils typically don't show up in oil analysis. So it appears like there's nothing. You have no phosphorus, you have no zinc, typically very, very little, if not no calcium as well. But there's an exception to phosphorus, and that is that sometimes we see it as an oils additive, but sometimes we see it as a greases additive. And the reason I mention this is that some systems have, greased parts, usually something like seals, that can have grease being applied to them, and some of it may migrate into the oil, and therefore it may show up in an oil that you wouldn't expect it to because there's a bit of grease getting into it. Another time, though, is sometimes during assembly, whether that's from original assembly or a rebuild, that the mechanic or the millwright might apply grease to some of the parts to either help hold them in place or lubricate them on their way in. And again, that may wash off and end up in the oil. So there we go, quick brief overview of elemental spectroscopy and a couple of elements that are going to come up in a second. But the next test I'd like to quickly review is particle counting. Now, particle counting can be done one of two ways. The most common way that most people are familiar with is called optical particle counting. And optical particle counting is a method whereby we flow oil vertically, as you can see in this picture here, in the blue section, through a very thin cell, and there's an intense source of light on the left, and it shines over to a CCD, like a digital camera type detector, on the right. And what happens is that particles, as they go by this beam of light, cast shadows onto the detector, and the optical particle counter sizes and counts the shadows, and that's how it determines the particles. Now, most people who discuss particle counting usually end the explanation there. I like to take it a step further, though. Question I would have is, how does it know how big the particle is based on the shadow? Meaning, what part of the shadow does it use to determine the size? Is it the longest measurement? Is it the narrowest measurement? Is it the average measurement? Well, it's none of those. What it does is, as that three-dimensional particle goes past the beam of light, as you would well expect, it only casts a two-dimensional shadow. So what it does is it does this neat little trick called spherical equivalency. So take a 10 by 1 micron particle, right? If it cast a shadow and it was 10 by 1 micron, what it does is it says, let's calculate the area. So the area of that rectangle there is pretty easy to calculate, 10 square microns. But what it supposes is it says, what if a sphere created that shadow? So a sphere is going to create a circle as a shadow. So it says what size circle will also produce a 10 square micron shadow. And to save you the math on this one, it works out to 3.6 microns. My point about this is, again, twofold. One part of my point is that 3.6 microns is how that particle gets reported to the instrument. As you can see, 3.6 is nothing like the 1 micron width or the 10 micron height. But the other part of why I point this out is that the instrument only reports particles 4 microns and larger. So in fact, that 10 by 1 micron particle would go by the detector and not get counted. It would see it, it would size it, it would recognize it, but it wouldn't throw it into the particle count because it wasn't a spherical equivalency of at least 4 microns. So I'm just trying to point out some of the, if you will, inaccuracies of the test. But the biggest inaccuracy really comes from the fact that a particle count doesn't tell you what the particles are. It just counts them. So there's no identification of the type of particles. Are they dust? Are they dirt? Are they wear metals? You don't know. The range that they're counted in is from 4 microns and up, and it typically cuts off somewhere around 200 microns. And the reason for that is that the film is only about 100 microns thick. So if the particle's much larger than about a spherical equivalency of 200, it simply wouldn't go through the detector. But the big interference to this test, other than the fact it doesn't actually measure the true size of the particles, is that anything else that casts a shadow can be counted. So water molecules, air bubbles, and even soft varnish particles can count as particles because they cast shadows unless we prepare the sample properly. And to do that, you'd have to dilute it, you'd have to sonicate it, you might have to vacuum it. There's quite a few steps that are involved there. So this might help some of you who have ever done an on-site or online particle count understand why it's always so much higher than what the lab gets. Because labs typically go through all these steps to prepare the samples, but portable and online versions do not. So that's one way of doing the particle count. But the other way, and this is the test oil preferred method, is something that's called pore blockage. And what we do is we use a screen like the one you see pictured here, and it's got some precision laser cut holes in it, and they may be 5, 10, or 15 microns. So say that's a 10 micron screen. Every one of those holes is exactly 10 by 10 microns. What we do is we push the oil through the screen at a constant pressure, but on the back side of the screen, we measure the flow rate. And specifically what we're looking for is the decay of the flow. So some people call this the flow decay method because that's actually truly what you're measuring. Point being that as the oil goes through the screen, any particle much larger than 10 microns in any one direction probably is going to get stopped by the screen. Now, as it lays across one of the holes, it doesn't necessarily cover the hole completely. So not only are you reducing the number of holes, but you're probably reducing the size of holes. So the particles that the screen is capable of trapping get smaller, smaller, smaller. So by profiling the flow decay, we can therefore, and I'm going to list this as a limitation to the test, we extrapolate every particle size from that singular measurement. So even though all the holes are, say, 10 microns, we can extrapolate that to show the 4, the 6, the 14 microns, and so on. So pore block really, just like optical particle counting, doesn't actually tell us the true size of the particles in any one particular dimension, but here's why it's the preferred method. It has no interferences. Air bubbles, water molecules, soft varnish particles, they all go through the screen without causing us any issues. They don't get counted. We don't have to do any special preparation to the sample. We don't have to take in any special account to the calibrations. We can push the samples through neat, and we feel like it gets us a pretty decent number. Now, saying all this, you're wondering how good is the number? According to ASTM for optical particle counting, these are the repeatability numbers. So if you look at the repeatability and reproducibility, I usually focus on the reproducibility myself. It's over 100%. meaning the value can change by more than double and is still considered the same value. So really, when it comes to most particle counting done by optical methods, I always say give or take a code. Because if you're familiar with ISO codes, then you know every time the code goes up by 1, the number of particles doubles. Well, the reproducibility of this test is essentially around 100% or more. So it means that honestly, the instrument itself could produce a value within one ISO code and still be considered the same number. So here's a quick overview of particle counting. The last test I want to breeze us through is analytical fluorography. This test is what we use kind of as a add-on compromise, if you will, to large particle analysis. Everything that won't be measured by elemental spectroscopy can be measured by analytical fluorography. So when we see a sample that's got particularly high wear metals or wear particle concentration, we automatically trigger an analytical fluorography, and this helps us see all the big stuff that otherwise might have gone undetected by elemental spectroscopy and potentially by particle counting. So the basic principle is we take a glass slide, just a little microscope slide, if you will, and we flow oil down it from top to bottom. It's on an incline. As the oil runs down the slide, in this picture from top to bottom, the particles will settle out from largest to smallest, and that's just fluid dynamics, how that works. But you're looking at that picture and you're thinking, yeah, but I don't think they'd form cute little straight lines. Well, they wouldn't normally, but we put a whole series of magnets underneath it. So all the ferrous particles actually do align magnetically into those straight lines. All the non-ferrous particles, on the other hand, will randomly distribute across the slide. So once we've prepared the sample by running the oil down the slide, separating out all the particulate, both metallic and non-metallic, we then take it and look at it under a microscope. So the limitation to this test is it doesn't care about particle sizes or what the metals might be. That's good. But it is a qualitative test because it is subjective due to the fact it's done by a human. So a human looks through the microscope and assesses the particles by what we call morphology, size, shape, and color. So they are able to see the size of the particles. If they're large enough, they can easily tell the shape of the particle. Are they, long and skinny, flat platelets? Are they curled up? And by color, they can tell, is it silver metallic versus does it look like brass? But also they can tell, has it annealed? Has it changed color? Things like this help give us some guidelines into the basic interpretation I'll show you next that categorize what particles are being seen by the wear mechanism that created them. The nice thing about this test is there's no significant interferences, and if you're concerned about the accuracy of the test, well, it is subjective. So we try and train our people to be very repeatable amongst the team, but again, it's a human. Some people might perceive something a little bit differently than others, so there is some subjectivity to the test. So in short, you're looking at everything under a microscope. By the size and the shape and the color, you can determine the wear mechanism that created it and the severity of that particular problem, largely driven by the size. So ASTM requires categorization of what you see into the following. So here's just a brief overview of what would appear on an analytical fluorography report. Of all these categories, and you're going to see about a dozen of them, the first two, rubbing wear and rolling contact fatigue, are the only two that could ever be considered normal. This is the type of wear material you might see under normal conditions. The only qualification is that typically if it's normal, it's small, it's under 5 microns. If it's much larger than 5 microns, typically it's an abnormal wear mechanism anyway. The rest of the ones I'm going to show you were always considered abnormal. So quickly, there's rubbing wear, which is just kind of a sliding wear, or like what some people call adhesive wear. Rolling contact fatigue is a rolling type of wear, so this would occur in rolling element bearings. But after that, everything else is considered abnormal. So cutting wear is usually what some people would call 3-body abrasive wear. That's never a good thing. Severe wear is a category that means the particle doesn't fall into the first 3 categories, but is still fairly large and has a particularly long, skinny ratio dimensionally. Chunks is the honest to goodness ASTM category For the fifth one, meaning it didn't fit into the first four, if it's any metal chunk that doesn't fit into the first four categories, you just automatically call it a chunk. If it's spherical, well, that's a particular type of rolling contact fatigue that may create that. If it appears to be from corrosion, we can list it as corrosive wear debris for anything other than ferrous corrosion. That falls into the one at the bottom there, as you can see, red oxides, just a fancy way of saying rust. But in the middle there, dark metallic oxides, that's never a good one to see. That is usually a significant and severe form of adhesive wear, where two surfaces come under such great contact with each other, they actually temporarily weld to each other. And then as they tear apart, the heat that's generated usually anneals at least one of the metals, and you get these darkened particles. It's nasty. Nobody ever wants to see that one. Dust and dirt is a pretty self-explanatory category of anything that appears to be from an airborne type contaminant, be it dust, be it dirt. Usually they're translucent, usually they're crystalline in shape. And then there's a catch-all category called other. And other allows us to put anything that didn't fit into any of the previous 10 categories and say, here's what it is. We think it looks like a paint fleck, it looks like a filter fiber, it looks like, insect wings, who knows, pollen, could be anything. The last category is not required by ASTM, but at Test Oil we do use it, and we just separate out oxidation byproducts, things that look like they might create varnish. Now that should normally fall under other, but we separate it out so it stands out just in case that seems to be what we're seeing. But anyways, those are the three tests real quick: elemental spectroscopy, particle counting, and analytical ferrography, just getting everyone onto the same page as to what we expect to be able to understand when we read a report. So here's the unconventional steps, as I call them, about how to read a report. So step number one, very simple step, sounds easy, it's much harder to execute than you think. Read the whole report. Top to bottom, start reading the report, move from left to right, work your way from the top down to the bottom. Don't skip anything. And you'll see why I emphasize this. Because a lot of people just jump immediately to the highlighted values and they're missing the bigger picture. But my other thing about reading the whole report top to bottom is I want you to be methodical about this. If you're methodical, you follow this set pattern, you'll get yourself through the whole report, because you can't make a judgment until you've seen everything, right? So we don't interpret as we go. Now, as we read the whole report, when we get to the actual data section, decide if any of the values appear abnormal. And that could be for any reason you like: too high, too low, too different from the new oil baseline, significant deviation in trend, or just a value you just don't like to see. Doesn't matter what your logic is. If you decide it's abnormal, here's all I want to do next. Categorize it into a cause or an effect. That's it. Don't decide what's causing what. Don't decide what's an effect of what. Just say, is this caused by something greater? Then it's an effect. And you go, no, this is the driver behind other things, then it's a cause, right? Cause or effect. When we get to the bottom of the report, after having reviewed all the data, we're going to find that all those causes and effects will group together into one or two causes, never more. What we then will do is decide on the next corrective action, or maybe we can identify what went wrong in the situation. When you're thinking about what to do next, I will caution you on this, and this doesn't apply to today's example, but I will caution you that changing the oil is almost never the solution. So many times with other examples I go through, people send me a report and say, what do you think of this one? Should I change the oil? I always kind of take pause there, because I'm like, well, yes, I understand where you are. The results are high. You don't like them. Changing the oil would certainly reduce them. It doesn't fix anything though. Right? We need to know what will fix something. So we may still in the end decide the oil has to be changed because we can't live with it, but understand that simply changing the oil just makes for a better report, doesn't make for a better machine. The example we're going to go through today, that won't be relevant, but I like to point it out every time I can. So we're going to go through an example now, and here's the example. So before we dive into this, I know some people listening probably don't know everything about a test oil report and its overall format. So let's cover a couple of quick things before we get into the actual reading of this report. So first and foremost, just understand that when we do get down to the actual data on the report, this column here is labeled new oil. It is the baseline information for the type of oil identified just above the arrow. That is populated by people that send in oil samples. So when you send in an oil sample, you also send in a sample of that virgin product, unused, straight from the drum tote, however you got it, as a baseline. This is not information that we get direct from refineries or oil blenders or anything like that. It comes from the end users who send in the other samples. And we typically recommend that it gets sent in about once a year. It does not have to be any more often than that. It's not with every batch of samples, but that is how it gets populated. So sometimes you may find that these things become out of date, and it's because, well, we haven't received a sample of that particular product in its virgin state in a while. So just letting you know, one, what that column is, and two, how the information gets there. But beside this column, this is where we see the most current oil sample. And that's the one we'll focus on as we go through the report. But what you're going to see to the right of that column is an older sample, and to the right of that, an even older sample, and so on and so forth. So really, when you're looking at trends, you read these reports from right to left. That's how you see the overall trend. But what you're comparing is always, of course, this most current sample, not only to the trend to the right of it, but to the new oil to the left of it. And that's why it's formatted in this way. So without further ado, let's actually read this report. Now, I'll just get out my little laser pointer here because I want to make sure we're following along and we're actually reading the whole report top to bottom. So we do start all the way up here. You read the report from top to bottom. You start off, it's a plain bearing, it's a 5-gallon sump, uses a Conoco multi-purpose R&O 68. I know it seems silly that we're reading all this, but you know what? Just that last statement I said, I know 4 things about this oil. As soon as I read that it's an R&O oil, I know that that means it has no phosphorus, no zinc, and probably no calcium. There's 3 things about the additives that I can tell you. Since it said it was a 68, I can also tell you the viscosity at 40 degrees Celsius should also be 68. So I'm setting myself up for what do I expect to see later on the report. All right, if I don't see what I just said, then right away I can tell you there's something wrong with this lubricant. It happens to be a Dodge sleeve oil bearing. This is just the sample information the day it was received versus the day the report went out. And I always tell people, look, I know it seems silly to read the customer information because this is going to be the end user's name, address, but this helps make sure you know it's your report, that this is the report you think it is for the machine you think it is, so on and so forth. When we come down over here, the list of problems, these are all the problems that were identified by the lab. Now, I will point out at this moment that these problems were found by the lab when this report came through. I have removed all of the colors though. Normally there'd be stuff alarmed on the report. I've removed all that highlighting because I don't want us to be distracted by that. I want to show you to focus on everything, not just the highlights. But it did say excessive wear and excessive particle count were 2 of the problems. Over here, these are comments related to an excessive particle count and excessive wear. Now, we'll see this in a little bit, but this is what I always describe to most people as a basic interpretation. This is what the lab is able to provide sitting in their office hundreds, thousands of miles from your sample point. They don't know everything, so they're going to make some middle of the road comments regarding how to handle, in this case, a high particle count and the high wear. So they don't necessarily know if their answer is spot on, able to be applied. So if they tell you that maybe you should think about changing your filters, you may come back to them and say there are no filters on the system. The point is they're only able to make a reasonable guess with what they have. And this is why I'm going to stress later why the end user should be the one to read the report. They may know things that would give better insight as to what to do next. But anyways, there's the problems, there's the comments. Now let's get ourselves down into this section here. So date sampled, if we start with the very first sample on this report, it is from October 2007. Then about 14 months later, we have another sample. Then about 18 months later, we have another sample. So not the most consistent sampling interval so far, but you notice this last sample is only weeks from the previous one. And the reason behind that is right up here in customer notes. This is a post-failure sample. So thankfully, with today's example, we don't have to figure out if there's a problem, because we know there is. This bearing already failed. It's catastrophic failure. This is a sample of the oil recovered from the failed bearing is what's going to be populating this column here. We need to see if we can figure out why it failed. So when we read down the other information here, you will see that we have the machine and lube condition. So this is populated by either the letters N for normal, M for marginal, or C for critical. So we have a critical marginal, normal marginal, critical marginal, critical marginal. And again, it's in the order of machine followed by lube. So we've identified the machine in critical condition for the last couple of samples, the lube in marginal condition for the last 4 samples. So it seems like we've probably had some warning signs along the way that things weren't looking right with the lubricant, and inevitably the machine went critical. And like I said, up here it tells us it did fail. So there's some hints as to what we're about to see. Under lube hours and machine hours, you will notice that it wasn't filled in on this sample. The hours for the lube oil in the machine were identical for this sample, and they're identical for this sample, but they happen to be lower. So either the oil and the bearing were changed, or maybe one of these numbers wasn't reported correctly. I don't know. And in any event, the last one wasn't filled in. They're all over the place. That's not providing us with any helpful information. So this is my mild jab at those people who are the ones filling in the information for samples. You need to fill this in accurately. Otherwise, this is kind of useless to us for today's example. But now let's get into the actual oil analysis report. So where we see the data, we're just going to start right at the top, and we're going to read down. We're going to identify things that seem abnormal to us. And as we go, we're going to classify them as a cause or an effect. So the first thing we see on this report that we probably don't like is iron. Right? Now, iron, reason we don't like iron, look at the sharp jump it did from the previous samples to this current sample. Huge, huge increase. Question is it a cause or an effect? Well, something made this machine wear, right? Could be an imbalance, could be an alignment issue, could be contaminant, could be low oil, who knows? Point is, wear is almost always an effect. So we're going to say iron is an effect. Okay, we return to the report. Next thing we identify as we move down the report, copper. Copper, again, just like iron, jumped up in the last sample significantly, way above the normal trend. Is it a cause or is it an effect? Well, again, it's just going to be an effect. Keep moving down the report here. Next thing we see is lead. Lead also took a significant jump from the last sample. So lead seems abnormal. Is lead a cause or an effect? Well, we'll just throw it right in with iron and copper. It is also an effect. We keep going down the report. Aluminum has been a flat trend the whole time, so nothing to say there. But as soon as we get to tin, my goodness, that one's really jumped up. So that is definitely an abnormal value. Is tin now a cause or effect? Well, just like iron, copper, and lead, tin's going to be right under there with effects. If we keep reading down the report, we're going to get a whole bunch of blanks because those are all below detection limits, but then we do actually see a value at calcium. Now, calcium has had a significant jump in the last couple samples, and according to the new oil line, there shouldn't be any calcium. So as I said before, when I saw there was an R&O oil, I knew that should be the case. This oil should not have significant levels of calcium, phosphorus, or zinc, but we do see an increase in calcium. So that seems abnormal. Now, is calcium a cause or an effect? Well, if you recall, what I said calcium was most likely sourced from in an elemental spectrographic report is from an additive of a lubricant. So does a wrong lubricant getting in here seem like a pretty reasonable event to trigger perhaps a failure? Quite possibly. So let's call calcium a cause. So we actually have a cause now. We keep reading down the report and we're going to get to phosphorus. Also, much like calcium, significant increase in the last couple of samples, also really shouldn't be there in an R&O fluid. So this seems pretty significant. Is it a cause or effect? Well, we're going to group that one right with calcium. It is also a cause. So in this first part of the report here, we've identified 2 causes that seem closely related and 4 effects. If we go to the next part of the report, where do we see an abnormal value? Well, we really don't see one as we go down the report until we get to the particle count. And this particle count is sky high. When you see all 9s in the data below, that is because it maxed out our instrument. So really the particle count is actually probably higher than the reported value there. That's just simply the highest this instrument is capable of reporting. So we have a catastrophically high particle count, but this is now a tricky question. Is that particle count high because maybe it represents contaminants getting in that led to the failure that we know this bearing experienced? Or are those particles actually all the wear material from the failure? So since we can't really answer that question conclusively at this moment, let's skip particle count for now and come back to it. So if you keep reading down the report, you're going to see that viscosity is perfect. 67.9 is the current value. I'm looking here for anyone not following. This is an ISO 68 oil, so that viscosity is bang on where it should be. I point this out because it's curious. Calcium and phosphorus appeared when they shouldn't be there. That is a very common sign of the wrong lubricant getting into the system. But my point is, it didn't seem to affect the viscosity. Now, there's really only 2 reasons that a wrong lubricant would not affect viscosity. And the number one guess would be that the wrong lubricant has the same viscosity. That's a very good guess. It's not the answer to today's problem, though. So for those of you thinking about this, try and think of a different reason you could have the wrong lubricant but not affect the viscosity. If we keep reading down, acid number has been fairly consistent and there's been no signs of water. So we go to the last part of the report, and that's where we get the analytical ferrography. And the first number that would jump out as a number we don't like, that we consider abnormal, is the rubbing wear. Now, I did say rubbing wear could be considered normal, but I stressed only if the particles are small. Well, these ones are in the 30 to 50 micron size. They're nearly visible. That's pretty large. So this is not a good thing to see, but is rubbing wear a cause or an effect? Well, funnily enough, just like the iron, copper, lead, and tin, it is also simply an effect. Something is making this thing wear, and that's just one of the ways it manifests on the report. They're all effects. The next thing on the report we don't like is going to be sliding wear, because anything beyond the first 2 I said are always, always, always abnormal. Sliding wear is always abnormal, but this one's really abnormal because the particles are even bigger. This is catastrophic wear particles, but it should not be too surprising to us because we do know this is a post-failure sample. But anyways, is sliding wear a cause or an effect? Well, it will be, just like the other ones, an effect. All of these are just effects. The last thing on the report that we have of note is dust and dirt. Been identified as very heavy concentration of dust and dirt particles appeared on the ferrogram slide. This is not normal. Is this a cause or an effect? Well, this is actually going to be a cause, right? Outside contamination getting into something like a bearing, probably what led to a lot of that wear that we're seeing. So that is definitely under cause. Now, since we've reached the bottom of the report, we should return to that particle count that we skipped. So particle count, we identified abnormally high. Now that we've seen everything on the report, can we come up with a reasonable conclusion as to whether or not that's a cause or effect? I think we can. Knowing that there's such a high level of dust and dirt, let's throw particle count under cause as well. And now that we are able to look at the final tally, I'll group them like this. Calcium and phosphorus seem to be related, as in the wrong lubricant's gotten in there. Dust, dirt, and particle count also seem to be related, but are a separate cause. So I've grouped them a little bit differently. Now my point is showing you this final tally, so you've got it all clear here. Everything we identified as abnormal on the report was listed here. This is what I want us to do. Ignore the effects. We don't need to focus on the effects. We need to focus on the causes. It's not because we know this bearing already failed that we don't have to worry about the effects. The point is you never have to worry about the effects if you don't fix the causes. So we need to focus on the causes. So this is where we'll spend our time in the last part of our discussion. So before we get too far along trying to think of what would cause calcium, phosphorus, dust, dirt, and particle count all to rise significantly simultaneously and lead to a catastrophic failure, let me give you one of the two reminders I said I would give. My first reminder is to keep things simple. And the easiest way I have of explaining how to keep things simple is to tell you a bit of a story. So I don't know if you've heard of Occam's razor, but the idea behind Occam's razor is that if you shave away all the unnecessary assumptions, whatever's left over will reveal itself to you as the simple, kind of an elegant solution to a problem. And you've probably heard Occam's razor paraphrased in one form or another because it does appear in literary examples. And like Sherlock Holmes has this quote here, and you've heard it said that if you eliminate everything else, no matter what is remaining, however improbable it is, it must be the solution. Well, here's the quote. So the point is, as we go through this example, we do probably need to, think a little bit outside of the box. So to help us understand how to think outside of the box, but also how to keep things simple, I give you a little bit of a story. So rather than telling you about Occam's razor, let me tell you about Occam's toothpaste. So this is a fake story, so don't think this has actually happened, but it's a funny way to help remember this. So we have ourselves a toothpaste factory, and it's losing revenue because some of the boxes are not getting filled with a tube of toothpaste. So empty boxes are getting shipped to the customers. Nobody's happy. So the CEO of this company decides to spend millions of dollars to solve this issue, and the way he did it was he put scales on the production line. So after the packaging has been completed, the box is then weighed. If the box is too light, it triggers a bell, stops the line, the worker removes the empty box, and they restart the line. Now, this seems to fix things because the toothpaste company doesn't ship the empty boxes anymore, and when they check the KPIs, the statistics show scales are catching hundreds of boxes in that first week. Now, a few more weeks go by, and the CEO looks things up again, and he realizes the alarm's not going off anymore. So his worry is, oh my goodness, somebody's turned off my special system. We're still shipping empty boxes. This is going to come hit us. We're going to start losing money again. He's not happy. So like any good CEO, he goes right down to the production floor to see firsthand what's going on. When he gets there, he sees no boxes in the reject bin. So this is now very worrisome for him. But what he does also see is just in front of the scales, somebody's installed a desk fan. And what he sees is that the empty boxes are being blown off the line before they can trigger the alarm. Right? There's your elegantly simple solution. Right? He installed millions of dollars worth of scales to weigh everything, and somebody else just came along and said, "Yeah, this is easier." And when he asked the person who seems like they might know something about this, why they did it, they said, well, they got tired of walking over and having to knock the box off and reset the line, and they just thought of something way simpler. And that's the point of Occam's razor. One is that the simplest solution is often the best solution. But as I said, we're going to have to think outside the box. Well, and this is where the joke answer comes in. Well, sometimes there is no box. Right? So keep your thoughts simple as we try and deduce this example that I just gave us. We need to think of one reason, one event, one issue, one singular occurrence that gave us that increase in calcium and phosphorus, because as I said, those seem to be related. And the most common reason for that is a different lubricant got mixed in. But I emphasize to you, no change in viscosity, right? So this isn't the wrong oil. Right? I'm telling you up front, that's not going to be the answer. But simultaneously, we also had an increase in dust and dirt as well as the particle count, meaning that for sure the lubricant's been contaminated. But the other reminder I have for you is that remember, we were sampling this bearing every 14, 18 months was the history beforehand, and then it catastrophically failed within a few weeks of the previous sample. So we need to consider whatever solution you think made this happen was created a very sudden, very catastrophic failure, right? It didn't just eventually fail. It was running more or less fine and then suddenly just piled right up. So many people who work through this example, one of the first things they suggest to me is this. They go, there you go. Somebody used a dirty top-up container or a dirty funnel or a combination of both, and there was a bunch of dust and dirt in there, and that got into the machine and it caused the failure. Well, that answer could explain the calcium and phosphorus if the wrong oil that was being used was in one of those jugs, and it could explain the dust and dirt and could explain some of the particle count. But do you really think that simply topping it up one day would suddenly cause a catastrophic failure? It seems a bit of a stretch. That's asking a little bit much of the amount of debris that might be on the rim of a funnel, might be at the bottom of an oil jug. Combined with that, yes, it may be the wrong oil, but it would have to be the wrong oil of the right viscosity. And the wrong oil type, but the correct viscosity, not likely to cause sudden catastrophic failures. So it's not a great deduction, and it's not actually the right answer anyways. But there's one other reminder I said I would give you. And if I give you this reminder, hopefully some people can maybe focus in on the correct answer. So my reminder was that the end user is always the best person to do the interpretation. Why? Because they can do what I call an advanced interpretation, right? The lab gives you a basic interpretation. The end user can give you an advanced interpretation. They know at least three things the lab would never know. They know the equipment configuration, like does it or does it not have a filtration system? Where is it located? What's the environment around it? What kind of conditions does it have? Things like this. And they also know if there was any maintenance done recently, right? Was the oil changed? Was the bearing replaced? All these kinds of things. So with this kind of knowledge, they always have a bit of an ace up their sleeve to really do a much, much better job at it than any lab would ever do. So now if you take what we're trying to do, trying to come up with one single event that caused everything to happen. We're going to keep everything that I previously described, the calcium and the phosphorus, probably wrong oil, no viscosity change, dust, dirt, and particle count increasing. But now we're going to add in end user information. The end user knows this operates in a dry but very dirty environment, right? Imagine a pulverizer, a crusher, something like that. Nearby, there is debris falling on top of this bearing at all times. It's practically buried in material. The other thing that they know is that this bearing housing has seals that require periodic greasing. This is the grease they use. Now, I know you can't read that label, so let me just zoom in a little bit here, but right at the top line underneath where it says NLGI grade 2, it says the grease they're using on the seal is an extreme pressure calcium sulfonate grease. So the answer to our problem that explains everything is understanding this is what the bearing looks like. Right? In here, we have the oil that was being sampled. This is where the oil would go in. But when this is all assembled, there is the Zerk fitting for the seal that goes around the shaft on this side, and there's also a Zerk fitting for the seal on the other side. At some point, somebody has over-greased that seal and blown it out. And some of that excess grease went into the oil, which explains the calcium, the phosphorus, but without the increase in viscosity. The blown seal then explains why the dust and the dirt and the particle count substantially increased to the point where basically it just abraded the bearing till the point of failure. And that is the simple improper lubrication and how you could catch it on an oil analysis report. And if we were to go all the way back to the oil analysis report, you would see evidence of that overgreasing had been there since the very first sample. This problem should have been caught 3 years before it happened. Now, I'm not saying it took 3 years to manifest, but at some point over the course of samples, I'm guessing right before the last sample that we were looking at, that was the catastrophic fail sample, but after the sample that was beforehand, somebody re-greased those seals. And in that event, in those roughly 6 weeks that transpired, that was when the failure actually took place. But evidence that it was being over-greased had been there for 3 years. So, like I said, I'm not saying it took 3 years for overgreasing to manifest itself. I'm suggesting it took less than 6 weeks for the actual really significant overgreasing to cause the problem. But evidence that there was some overgreasing had always been there. So with that, I'm at the end of the presentation. I do thank everyone who's been listening the whole time for your attention. And if there's any questions now, I'll turn it over to Heather so she can read them off to me.
Hi, Evan. Thank you so much for that. That was great. It looks like we do have a couple questions. Our first one here is from Edward, and he says, ferrographic techniques have a limitation for organic iron contamination. Can you comment on any ICP methods for organic iron analyses?
Ooh, that's a good question.
That is a good
I,
one.
I would say that without getting into some really specialized spectrographic methods, yeah, you're not going to see that from most commercial labs. We all tend to use fairly comprehensive, I guess would be the polite word, instruments that measure multiple elements simultaneously. So we tend to favor ICP over, say, like AA and rotating disc electrode, but we just use standard ICP. We don't get to mass spec levels of ICPs. One, it's a very expensive instrument, and two, it's just more time consuming per sample. So from a throughput perspective, yeah, I don't think any lab would really have a significant ability, I would say anyways, to be able to analyze for, yeah, those forms. But I guess where I would circle back on that question is how much do you think that matters? And maybe you've got a particular example, Edward, where that has come up. But for most of us, measuring the particles that we're expecting to find, we're expecting normal wear mechanisms to generate particles under 5 microns. That's what we're trying to detect. When you get significant corrosion or chemical reactions occurring in the metals, it tends to shed larger particles than the 5 micron range anyways. So just by a size limitation, they probably wouldn't get measured. And that's where you have to look to alternate methods like wear particle concentration, analytical ferrography, or even just a good old patch test to help capture some of that. And when we do patches, we can go to EDXRF then, and again, that can help identify the elements that are found on the patch that have separated out. So I don't know if that fully answers your question, but I guess my short answer would be I almost don't know if I'd worry about that because, like I said, I would expect the organic iron particles to be larger, and I would need to not expect to find them under ICP analysis. I'd probably expect to find them under some other test. But yeah, that's about all I can conjecture at this point.
Mm-hmm. I would agree with that. And the next question we have is, wear always considered abnormal at 30 micron sizes, considering the different clearance sizes of machine components?
Well, and that's where the limitation to ICP is not too much of an issue, because if you look into literature and say, what is the typical clearance of a dynamic moving part? I know two quotes off the top of my head. One says it's in the 1 to 5 micron range. The other one says it's in the 2 to 22 micron range. So there's a lot of overlap in that 0 to 5 micron range of capturing most of the particles that would be generated in most of the clearances. I would say anything much larger than about 10, 20 microns for sure is outside most clearances. I mean, obviously not like, say, gear teeth, but if you're talking about other lubricated things such as bearings, like today's example, no, they're going to be quite small. So 30 microns seems pretty big. That's a significant clearance.
Mm-hmm.
And it's not to say it doesn't exist in part of the machine somewhere. Certainly large scale machinery may have a large clearance on one side of the shaft, but a smaller clearance on the more load supporting side of the shaft. And that's where, the ranges come in, where people say 1 to 5 or 2 to 22 microns, because that's right out of ASME handbook shows clearances like that. So that's why we focus on that, and why ICP was developed to measure in that range, because it captures the particles we expect to find. It doesn't capture what we don't expect to find, but that's why we have to use alternate testing.
Mm-hmm. Yes, thank you. And then Mohammed has a couple questions. The first is, why don't we talk in the report about acid number?
In this example, the acid number was a flat trend, so it did not increase. It did not show signs that the oil was oxidizing. Also, in the example, the FTIR oxidation values were not changing. So that's why it was not talked about. Just, it was a flat trend.
Yes. And then looks like our final question for the moment. Uh, Mohammed also asks, how can we overcome the problem of not having hours on oil in the interpretation process?
The easiest way to overcome that is to simply rely on the calendar. Then, as long as samples are taken at consistent intervals, the assumption being the machine is operated consistently, not necessarily continuously, but consistently in the same interval. So even if it's only run 2 hours a day, if you sample it every 3 months, you know that you're going to get, roughly 180, 200 hours between every sample. And that as long as you continue sampling every 3 months, you're going to have that roughly 200 hours of oil and machine hours build up over time. You don't need to report it. It's just good that something is provided. But if it's blank or if it seems to be questionable, then all we can go by is the calendar and say, we're going to assume this thing isn't run so cyclically that 1 quarter to the next quarter, 1 month to the next month, or 1 year to the next year doesn't represent roughly the same amount of usage on both the oil and the machine. So that's the easiest way to overcome it. But yeah, preferably, of course, you'd always like it if somebody could even provide an estimate on the hours. I mean, understandably, hardly any machines contain hour meters or any sort of digital counters on them. But, we still like and appreciate if people can estimate it based on perhaps their SAP system
Hmm.
or just a basic assumption of this thing runs continuously. So 24 hours a day, it's been, X number of days, here's how many hours it is roughly.
Yes, I agree with that. And it's now an hour in, so I'm just going to ask one more question, and then for anyone who has additional questions, I will be giving them to Evan once we end the webinar today. And you can also find his email address there on the screen. If you're interested in more information, please always visit testoil.com. We have webinars approximately every 2 weeks moving forward, and we also have an on-demand section where you can watch previously recorded webinars if you're interested. And for our last question for the moment, uh, so is there an alarm limit for elements to identify the severity?
Short answer to that question is no. Um, and the reason for this is there's too many variables to suggest that, as an example, 100 ppm is severe. 100 ppm in 5 gallons of oil is less than 2 fingernail clippings worth of iron. 100 ppm in 50 gallons of oil is about 3/4 of an ounce of material. 100 ppm in 500 gallons of oil, on the other hand, is nearly half a pound of material. So if you were to look at 5 gallons with 2 fingernail clippings, 50 gallons with 3/4 of an ounce, and 500 gallons with a half a pound, and say, which one's worse? Well, from oil analysis perspective, because it measures concentration, they're all the same. And therefore, when you factor in that the sump size varies from one system to another, to try and say that all gearboxes should be alarmed at 100 ppm as an example, well, that's not going to fly. Some gearboxes have a very small sump of only a couple of gallons. Some have a couple hundred gallons. Some maybe do a shared lubricant system that could have over 1,000 gallons. So because these are all measured in concentration, it's very hard to establish an alarm limit. So rather, what you would do is you'd look at a deviation from trend. So typically, you're willing to accept anything that follows one standard deviation or less. Once you exceed 1 up to 2, that's kind of your caution. 2 up to 3, that's kind of your severe. And that's usually how most people would do controlled charting for just about anything. But that's common trend analysis, sort of statistical analysis way of setting an alarm limit is deviation from trend based on standard deviations. 1's good, 2, 3, take action. So hopefully that answers your question.
Perfect. Well, thank you very much for your time today, Evan, and thank you everyone for joining us. And again, if you have any questions, feel free to email Evan directly. Any questions we didn't get to, Evan will be responding later today. Take care and stay safe and healthy.